Okay, so last time we were discussing the following. We had defined the vacuum of the free theory, okay, or the ground state of the free theory, okay, which has 0 energy and 0 momentum that we saw. And we also saw that if we act with the A dagger k on this vacuum, I get a single particle state with momentum k, okay, and if I act with a string of A daggers, let us say n of them, then I generate n particles. Okay. Now, I will normalize this state to 1. So, I will say that this vacuum is normalized such that it is, if you calculate the inner product, you get 1. Okay, this you can always do. So, if let us say this was not 1, but some other constant, let us call it alpha, okay, then you can always define a vacuum which let us call nu is 1 over square root of alpha of the old one. Okay, so that when you take the inner product of this new vacuum that you have defined, okay, this will be 1 over alpha times this will give you an alpha, and which gives 1. So, you can always do that thing, and which means that we are free to choose to normalize the vacuum like this. Okay. Now, if you look at this thing, which I am saying it is a single particle state, if you multiply with multiply this thing with any function of k, it still remains a single particle state with momentum k, because what counts is this operator acting on the vacuum. What other function you multiply in front of it is immaterial, and that freedom we can use to define what the normalization of single particle states we want to choose. So, I will choose the following. Okay. So, I will choose to define a single particle state with momentum k by this notation. So, if I write a k in this ket, that means a single particle state, and of course, it has to have this. And for the normalization, I can choose some function here, and that I choose 2 omega k, square root of that, where omega k is as before k square plus m square. Okay, that is a choice, and not everyone makes this choice. Different authors will use different normalizations, but you are free to choose whatever you like, and you have to just consistently follow your normalization. Okay, so, this is what my definition of a single particle state would be with proper normalization. Okay, so, this we should remember. Now, let us see if we choose such a normalization, what do we get for an inner product of these two single particle states. So, if I take this, then ket k is A dagger k acting on ket 0, then your this state, okay, is obtained by taking, okay, so I have forgotten a 2 omega k, let me write it down in the next line. Okay. Then if I take the p here, it will give me a 2 omega p, the square roots, okay, and you will have, instead of A dagger, A of p and the vacuum again. Okay, so, this is what the expression is, and if you take the this quantity, I want to bring A dagger to the right, and that I can do by using the commutation relation, and when it comes to the right, it hits the vacuum on the right and kills it. Okay. Equivalently, the A dagger, when it goes to the left, it hits the vacuum to its left and kills it. So, whichever way you see, it is going to kill it. So, I bring it here, but in doing so, I have to use the commutation relation, and that gives me delta function, another term with the delta function, and only that delta function term survives and gives you the following. So, this will lead delta cube of p minus k, delta cube of k minus p, and only that term survives, and that delta function you can use to set k is equal to p or p is equal to k, up to you. So, you will have this delta cube k minus p, okay, and then you will have the vacuum from the left and the right, and that gives you 1 because of this condition. So, that is 1 times 2 omega p. Okay, that is what you get. If you wish, you can also write it as 2 omega k delta cube k minus p. You can do so because you have a delta function here. So, whether you write p here or you write k here, for the argument of omega, it does not matter. Okay, so, that is how our states are normalized. So, let me write it down here. Okay, maybe I will later collect all these results. So, this is good. These are single particle states with precise momentum defined. Okay. But we also want to see particles that are localized in space. Okay. And of course, you know, if you try to localize the particle in space, it will spread out in the momentum space. So, it will not have a fixed momentum, but its momentum will be spread out. Okay. So, we want to search for a particle which is localized at one point in space. Okay. Now, how are we going to find that thing? So, let me write down. What we are looking for is a particle localized in space and time also. Okay. You may ask that the particle is here at this time. Okay. So, that is what I am asking. Now, recall that you already know from quantum mechanics, and what we are doing is quantum mechanics, it is just quantum mechanics of the fields, is that if you try to localize the particle at one place, its momentum will completely spread out, okay, that we know, which means that I will have to integrate over all the momenta. So, I take single particle states of precise momentum, but I have to sum over all of the all the momentum. That is what we know. Okay. And so, this will, let me write it down, this will be a sum or basically integral over the momenta of single particle states Okay, this is what we will have to do. Also note that the state that you define, okay, should transform nicely under Lorentz transformations. Okay, it should have a proper transform. So, let me write that down also. Transforms nicely under Lorentz transformations. Okay, and so we are looking for such a thing, and of course, the second point, transform nicely under Lorentz transformation, is a guide, and of course, the first point is also a guide to searching for how to define a particle localized in space time. So, let us look at what we have already seen. If you look at phi x, let me act the operator phi on the vacuum of the theory, and if you substitute the expression for phi of x, which was d cube k over 2 pi 3 halves 1 over 2 omega k. I hope I am writing the expressions correctly here. And then we have a of k e to the minus I k dot x. Remember, this is a dot product of two 4 vectors. So, I am not putting arrow here. These are 4 vectors, plus a dagger of k e to the I k dot x, okay, and this acts on ket 0. That is what we have on the left. Now, of course, this quantity what you have on the right transforms nicely under Lorentz transformations, because phi of x is a scalar. Okay, and also we assume that the vacuum remains unchanged under Lorentz transformations. Okay. So, this quantity on the left has a nice transformation property. So, our second criteria is definitely met, but let us see whether this is a sum of single particle states of definite momentum, and that is indeed the case, because if you take this A and act on the vacuum, it kills it. So, that term is gone, okay, from this expression, and what you are left with is just this A dagger k, and A dagger k acting on the vacuum is what gives you single particle states of definite momentum, of momentum k. Okay, so, let me write this down by 2. Okay. Now, I will use the normalization that we have already given for single particle states here. So, A dagger k acting on vacuum gives you single particle state k divided by 2 omega k, or whichever way you see. I can then multiply and divide this thing by root 2 omega k, which will give you 1 over 2 omega k, and that root 2 omega k combines with A dagger k and ket 0 to give you the state k, single particle state of momentum k, and you have e to the I k dot x. Okay. Now, if you see that this is satisfying our both the requirements that we wanted, okay, and clearly this is representing a particle that is located at point x at time t, right. So, this I mean, if you are still not feeling very happy about what I am saying, you can try to map it to what you know from single particle quantum mechanics, okay, and see that this is indeed in the limit where in the non-relativistic limit, this indeed gives you what you have learned in your quantum mechanics course. Okay. So, it goes down, it gives you the same thing apart from some overall factors of this omega k, which you did not have there. So, anyhow, this is clearly representing a particle that is localized. Let me write x in or t comma x. Okay, so, I hope it is clear that this indeed represents a particle localized at x at time t. Okay, so, that is the that solves our search. I mean, this completes our search for how to write down a particle localized at a particular space time point. Okay. So, this also we should remember. Okay, let me do some very trivial and simple calculations to get some familiarity with manipulating these quantities. So, something really simple. Suppose you are given a particle at point x and time t, okay, and you want to turn it into a particle at point y. How would you do that? You can just do an integral over d cube x, insert a delta cube of x minus y, okay, and then you have phi of x get 0. Okay, let us put t equal to 0 for the moment, it does not matter. So, that this is representing a particle located at x, and when I do the integral, it will turn it into phi of y. Okay, that was too simple. Actually, you could have just put y here. That is the same thing. Now, suppose I am given phi of x get 0, okay, and I want to, from here I want to go to a particle which is localized in momentum. So, right now the particle is localized in space, it is at x t. Now, I want to do something to it and turn it into a state which gives me a state of well defined momentum. Okay, let us say that momentum is p. Then I can do the following. I can take the phi x 0, phi x acting on the vacuum, and integrate over all of the space. Okay. If I am integrating the single particle state over all of the space, so I am taking it and delocalizing it in space, and when I delocalize it in space, I expect to get a localized particle in momentum, and let us see whether that has happened. So, here this is d cube x e to the I x dot p, okay, and let me again put t equal to 0, so that I do not have to carry around the omega k t term. This, and you have from the phi d cube k over 2 pi 3 by 2 1 over 2 omega k, and only the a dagger term survives from here. So, you have a dagger k e to the I k dot x is correct, and I have put t equal to 0. So, I am putting arrows here and this is correct. Now, I will combine this exponential with this exponential, okay, and do the integral over x, because I want to see how it looks like in the momentum space. Okay. Now, when I do that integral, okay, there should be a minus sign, because here it has e to the I k dot x when you have 4 vectors, and k dot x is omega t minus k dot x. Okay. Let me write this is omega t minus k dot x. So, you get a minus sign because of this. Okay. So, this is fine. So, these two exponentials combine and give you a delta function. And then you still have the integral dx d cube x and e to the I or minus I k minus p dot x. Okay, and this is what gives you a 2 pi cube delta cube of x k minus p. Right. Now, I can integrate over now I can integrate over k, that will turn all the k's into p's. So, I will get, and this of course 2 pi cube gets cancelled here. So, I have 2 pi 3 halves divided by 2 omega k, but k is turned into p because of the delta function. So, 2 omega p times a dagger k turns into a dagger p, get 0, okay, which is, if I multiply and divide by 2 omega p, then I get 2 omega p times this. Okay. Of course, I could have just instead of starting with this e to the I x dot p, I could have multiplied inverse of this constant factor, this factor which I am getting here in here, and then I would have ended up with p. Anyway, does not matter, it is the same thing. So, you see that by doing this, you can get a single particle state with precise momentum. Okay, so, I have been till now either talking about completely localized state in position space or completely localized state in momentum space, but we would also like to construct states which are representing wave packets which have which mimic the real particles which we see. I mean, there is nothing unreal about what I am saying about these things, but typically when you are doing an experiment, you have an understanding that the particle is here roughly and has momentum this much roughly within the limits of uncertainty principle. Okay. So, that kind of notion we want to see here, that is, we want to construct the wave packet which has a momentum around some momentum p. Okay. There is of course a spread and it has some location x, and of course, it is spread in space also, and that is what we want to construct. So, it will be of course something in between what I have done till now. So, this one, when I took this particle which was completely localized and I integrated over entire space with a factor which was, you know, if you look at the mod square of this, it is 1 everywhere, right. So, you are really spreading it out uniformly throughout the space, okay, and that is why you got completely localized state in the momentum space. So, instead of spreading it out uniformly over the entire space, I could spread it in such a manner that it has most of it is localized around some point, okay, and then the spread decays the moment you go slightly away from that position. So, that is what I want to do. Okay, so, this time instead of integrating e to the I, what was that, x dot p. Okay, now, I will not integrate with this factor, but I will integrate with minus x naught squared over sigma square. Okay, sigma, you need something here to absorb the dimensions of a length that you have in the numerator, because the exponent has to be a dimensionless quantity. And this of course, as you go away from x naught, okay, this piece is providing exponential damping. So, I take this factor and I integrate over all the space this quantity, right. That is what you will do to localize, not localize, but slightly spread around x naught, okay, because this piece was anyway localized. Now, you are spreading it around. Okay. Now, that is good. Now, let us see what happens. What I want to see now is that this indeed gives me a state which is also having a peak in momentum around some point, and then it falls off. That is what we want to see. So, that is not difficult. this guy is d cube k. Okay, let me not write 2 pi cubes and all those things. I'll also put t equal to 0 just to avoid writing many things. Then you get e to the minus I k dot x that we have seen, and you have a dagger k get 0. Okay. Now again I will do the same thing. I will combine these two, okay, and then do the integral over x. So you have integral d cube x e to the I x dot p minus k, but you also have x here, unlike the previous case where it was not there, e to the minus x minus x naught square over sigma square. This is the Gaussian, right? This is the Gaussian which you have. It's this bell shaped curve, and then you of course have d cube k. Let me write here, and a dagger k get 0. Now look at this space. The x dependence is solely here. Okay. This is just a Fourier transform from this is just a Fourier transform of this Gaussian function. And you know that the Fourier transform of a Gaussian function is again a Gaussian function. Okay, so this integral d cube x of this Gaussian is going to give you, apart from some constants, another Gaussian, but this time it will be p minus k whole square, and of course some constants will appear here. Okay. So what you get is d cube k. You can supply all these constants which I am omitting right now. Okay, d cube k e to the minus p minus k whole squared over some factors which you can determine. A dagger k get 0. Let me instead write k, because anyway I am omitting some factors. So I can just supply of factors of omega k or root omega k and turn it into k. So you see what you have here is again a sum of single particle states, which is again a single particle state. Okay. But then here, because you are summing over all the momenta, it is clearly spread out, but because of the Gaussian which is peaked at the value p, momentum p, the state which you have is really representing a wave packet which is peaked around momentum p, okay, and it spreads around. And also from here in the beginning what we saw, the way we constructed it, it was that it is peaked around x naught. Okay. So this function, this quantity, okay, it represents a wave packet peaked around, or peaked is fine, around x naught in position space and around p in momentum space. Okay, that is, I think, all I wanted to say this time. Yes, exactly. Okay, so we will continue further in the next video.